Hey, this is Chan Beauvais, your instructor for CIS 209. Our topic is relationships today, and we're not talking about personal relationships, we're talking about relationships or entity relationships. As we mentioned in the previous topic, we have three basic types of relationships. We have one-to-one relationships, which are infrequently used because typically you can just consolidate those two entities into a single entity. We have one-to-many relationship, which is probably the most frequently used thing you'll find. And then we have another instance of a type of relationship called many-to-many. And this occurs when an instance of the first entity is associated with many instances of a second entity. And for the second entity, it's associated with many instances of the first one. So we resolve this using an additional associative or intersection entity, as we'll see in just a moment. Here's an example of a one-to-one relationship. Let's say we have employees, or in this case students perhaps, and we have parking stalls. So each parking stall will have to have an ID. That's the primary key of the parking entity, and the student has a student ID and student name and student other data. And we could create a relationship between two entities where a student has 0 or 1 parking stall and a parking stall has 0 or 1 student assigned to it. So this is probably a classic case of where you would be well justified in going ahead and creating a second entity called parking or parking stall and creating the optional one-to-one relationship between student and parking. There is another way you could do this, a one-to-one relationship between student and parking, and that is to have one table, and you could call it student parking or you could just call it student. And here we have the student's ID, the name and other data, and then we have the parking stall ID with all the other data. The only drawback to this, if not all students have a parking stall assigned, then the parking stall ID would have to be an optional field. We wouldn't be able to require a valid data entry in there, so you have to make it nullable, as they say, which those students who don't have a parking stall assigned would wind up with what we call a null value, meaning nothing, in the parking stall ID column on their row. And again, null means no value has been assigned or is known for that. And there are issues when you write queries against null. They have to be treated very differently. We'll take a look at that in our SQL module, SQL topic. But anyhow, this is also an alternative. Just one problem there is that you have to leave the parking stall ID null for those students who are not assigned a parking spot. And just one final word on one-to-one relationships. In most cases, you find that the relation can be combined into one. Some database administrators would like to split these apart for security or other reasons. You do have other options, though, that can be applied. You could create views or do some other method to restrict access to the sensitive data you're trying to split apart. There is, however, a special case when applied to a modeling pattern called supertype-subtype. We'll see that the subtype is a 0 or 1 optional relation to the supertype when we look at modeling patterns. One of the most common type of relationships is one-to-many. So this is a case where an instance of one relation, that is an entity, can have many instances of another. The typical sample we use would be a customer being on the one side, can place many orders, and each order is a many-side relation to the customer. And again, an employee maybe can be issued many paychecks. The employee is the one side, the paycheck is the many side. Hopefully an employee gets many paychecks. There are some employees who only get one paycheck, but then I guess they didn't make it. Relationships need to be thought of from an instance base. So what you're asking yourself when you're testing a relationship is how many instances of employee are associated with a single paycheck. So an employee should be able to get many paychecks, but a paycheck is issued to one and only one employee. The instance of the paycheck is issued to one and only one employee. So we have the customer placing many orders. Again, looking at it from the customer's perspective, the customer can place many orders, but each instance of an order would be placed by one and only one customer. That would be utter chaos if an instance of an order was placed by many customers. Who are you going to ship that to? Would be the one question I need to ask. An employee can be issued many paychecks, but the instance of the paycheck is issued to one and only one employee. And this shows that the relationship is always a two-sided thing. You may have heard that before from interpersonal relationships, but we need to consider the direction of the relationship in both directions to make sure when we're reviewing this with our business subject matter experts that they come to agreement that, yeah, an instance of this has this many instances of relation on the other side. Many-to-many relationships are very common. The classic one I like to use is the student enrolling in the class. So a student should be able to enroll in many classes, even in one given quarter. Some institutions have caps on the number of credits a student can take in a quarter, but still a student should be able to register in many classes. And then a class can enroll many students. Now, what we see when this is done improperly is any attempt to put student data into a class entity or class data into a student entity will result in a repeating group of fields, and I'll show that to you in a minute. What we want to do is break this out into a third entity, said to be an associative or intersection. Some people call them linking entities. But a third entity is required to resolve the many-to-many relationship properly. And here's an example of what might happen if you incorrectly try to force a many-to-many relationship into one table or another. We could wind up with a student class entity or a student entity with, again, the student ID and the student other data, and then you'll see this set of repeating fields. For class 1, there will be an ID for that class. A quarter the class was taken in, a grade that was issued in that class in that quarter for that student. Then you need, for the next class they took, another column set of repeating fields, class 2 ID, class 2 quarter, class 2 grade, etc. ad nauseum. Or you could flip it around, this might even be worse, that the class, if you try to force the student data into the class, you have the class ID and name and other data. And then student 1 ID, student 1 quarter, student 1 grade, student 2 ID, student 2 quarter, student 2 grade, up to student N ID quarter and grade group of repeating group of fields. So you can imagine if you have a class that's had 1,000 students take it, you'd have 3,000 columns. That just doesn't work. That should be pretty obvious. So this is the way we would correctly resolve a many-to-many relationship. You have a student entity and a class entity, and then you have another entity called enrollment, which satisfies the many-to-many relationship. One type of key structure we can place on the enrollment entity is to have both the student ID from the parent-student table and the class ID from the parent-class table participating as a combined or concatenated composite key. Then the other data you might want to put in there is the grade they were assigned. We don't need the quarter in there because the quarter is an attribute of class. So this kind of solves several problems at once. Any other data that would be about the combination of the student having taken the class would be fair game to go in the enrollment, except for any kind of calculated thing. We might be tempted to put number of days attended, but that would probably be better suited to put an attendance entity in as a many-side relation to the enrollment. Anyhow, this is what it should look like. And notice what we've done here. We've taken the enrollment and created a one-to-many relationship between the student and the enrollment, and again, another one-to-many relationship between the class and the enrollment. So this breaks down into a set of one-to-many relationships. So again, let's take a look at how we might want to key this. The associative entity can have as its primary key the concatenation or combination of the primary keys of the two parent relations. That would be student ID and class ID in the previous example. And so for those two attributes, each set of those attributes must be unique. So I could have for any given student multiple class IDs, for any given class multiple student IDs. What I wouldn't allow is the combination of student ID and class ID to be identical for two different rows, because then I would be violating the uniqueness principle on the primary key for that row. Any other data that's about the student and class or grade also goes in the associative entity. So you want to be careful and make sure that any and all data that's in an associative entity is about the combination of the two entities that have the many-to-many relationship. So one other thing we want to talk about is how entities participate in relationships. This is called cardinality. We want to determine whether or not the relationship is mandatory or optional. As we look at the transactional pattern a little later, we'll show you that an order must have at least one but can have many order details. So that's a mandatory relationship. An order doesn't do you any good if it has no ordered items on it. So we have a mandatoriness. Most relationships are optional in that a customer places 0 to many orders, meaning they can be a customer before they've actually placed their first order. If you turn that around and the business told you that that relationship must be mandatory, then a prospect perhaps becomes a customer when they place their first order, but a customer places 1 to many orders instead of 0 to many. So you can see it's about the optionality or mandatoriness of the relationship itself. These are determined always by business rule, and you need this business rule to be called out and documented for each and every relationship you have. There's another thing called degree. Is there a maximum or a minimum? I love to use the sports match. For instance, a baseball game is played by 2 and only 2 teams. Has a minimum of 2 and a maximum of 2. So that's called the degree of the relationship. And the last issue we want to talk about in this topic is integrity. So we think of integrity in 2 ways. Within the relation itself, the data can have no duplicate records within a given entity. The fields are consistent within their domain. So no field has a domain violation. For instance, somebody tries to put a numeric age in a date of birth field. So those domains, if it's a birth date, all of the data throughout every row in that column is a date, and a business rule constrained date. And then you have business rules involving 2 or more fields. We call those correlated attributes. For instance, the order date on an order probably should be before the ship date on the order. The ordered quantity on an order probably has some determining factor in the shipped quantity. I would think that a shipped quantity needs to be between 0 and the ordered quantity. I certainly don't want to order 10 of something and get 50 of them shipped to me. So those types of business rules with correlated attributes need to be in place. And finally, referential integrity has to do with relationships. We have no orphaned records, which means no row in a many-side relation without a corresponding row in the one-side relation that links it. So this restricts us from deleting rows in the one-side relation that have many-side rows in the many-side relation unless we delete all of them at once. This is called cascading deletes. So we'll be talking about that again as well. Anyhow, that's it for this topic on relationships.